Welcome to our webinar on Automotive Cybersecurity, which I'm going to present today. My name is Christoph Ebert, and I will present together with my colleague, Youssef Rekik. We are active in Automotive Cybersecurity with Vector since many years, and we regularly present also these webinars. Each webinar, even with the same title, has completely reworked content. So if you've heard the webinar before, don't worry, it's different. We talk about new standards like UNECE, we talk about new experiences, and it's certainly worth to listen in. This webinar is part of a series of webinars. We have webinars on functional safety, on other topics, and also with respect to cybersecurity. We dig more into cybersecurity topics like in the scope of AutoSAR, also in terms of how to do specific testing methods. So you find all these webinars recorded, freely available in our media center of Vector. With that being said, let me start. And first, a very short introduction on what we are doing. Vector is a global market leader in automotive electronics, in software and engineering tools. We have, in the meantime, more than 3,000 people worldwide. We work in different domains with the consulting, of course, in automotive, but also medical, IT, and other critical systems. And my responsibility is managing director in the consulting services of Vector worldwide. And my colleague, Youssef Rekik, who will also be present in this webinar, is security consultant and has a wide experience in this topic. He will be addressing your questions in parallel, so you can use the chat service as long as you are in the online version of this webinar. So you can directly ask questions which Youssef Rekik will answer to you. At the end of the webinar, this is also part of the recorded version. We will summarize some of the key questions which you receive. And on those, for those of you who listen only to the recorded version, obviously there is no online chat, but feel free to contact us. You see here our URL, which is www.vector.com/consulting, or just join us with Twitter at VectorVCS, or send us a mail with any question or need for support. The webinar is structured into 4 parts. I will first talk about the topic of risk-oriented security, because this is the core of any cybersecurity activities. We will then look into systematic security engineering, a snapshot on some engineering methods, and finally a set of case studies, some experiences from our many security projects, and also some outlook with some important topics to close up. I would start with the current situation in the market, and what you see here is the result from our survey, which we have been doing at the beginning of this year with our customers, and there we always ask the same question: what are your short and long-term challenges? And one important part in this feedback was that we have, in the both short and long term, key focus on cost and efficiency, very closely connected with quality, that is safety, security, and competences. That means, in a nutshell, we have a very dangerous connection of extreme pressure on competitiveness with cost, high need in terms of quality because of product liability. This is exactly our topic here with cybersecurity, and a lack of competences and knowledge. And this gives a risk of a vicious circle, because if due to the cost pressure, we won't follow with the competences which are necessary, we sooner or later lose speed with innovation, with quality. You see this red circle on the left side. This is perceived as a long or midterm challenge, but not so much short-term, because short-term will be eaten by cost pressure, by quality demands. But that means if we don't have the budget, if we don't have the competencies available, we will sooner or later be disconnected in terms of innovation. And this is the real challenge which we face currently in industry with our customers. And that's something to keep in mind. We bring in lots of experiences in efficient implementation of cybersecurity. And I will give you later on examples from our own work, such as our gray box pen test, which is far more efficient than the classic black box pen test. And we have several such topics also, for instance, for TARA, for platform-specific security analysis, etc. And this would be topics where you can also address this cost and efficiency need, and at the same time beef up your cybersecurity. So that's at the heart of this webinar, and this is, if you want, also one of the first changes which I want to emphasize compared to the 2019 situation, when we did not have yet this dramatic picture of vicious circle. And of course, at the moment, it's amplified, where we have travel restrictions due to the corona pandemic disease, and that means even more cost and efficiency pressure. And people working from home, of course, also means the efficiency need is even higher than at the beginning of the year when we did this survey. So stay tuned, because this is exactly where we can help you with our competences. Now, the connection of functional safety and security is quite close. And for that reason, let me briefly address these three topics of functional safety, of cybersecurity, and of privacy, because they relate to each other. The common denominator is they are all, if you want, hazards or threats to what we are doing in engineering. If we don't pay attention with risk mitigation, then we will have safety problems. The three topics are also connected because one fuels the other. That means if we have a functional safety analysis and a safety requirement and a safety goal, which is implemented by certain software and or hardware, if this software can be impacted by security attack, then our safety goal is not anymore liably achieved. And this means the whole functional safety exercise which we have been doing would not anymore be valid. And this is then a big product liability topic, because obviously the functional safety depends on software which works exactly in line with what we have specified as safety goals. If the software is corrupted, if the software would not work as it was specified because of a denial of service attack, because of other security challenges, then functional safety is not anymore guaranteed. So clearly, here's a very, very close relationship. I come back on that later, because that's one of the efficiency levels which we see, that combining functional safety and cybersecurity benefits from not only a reuse of existing infrastructure and process, but first and above all, that it effectively mitigates your product liability risk, even in times when you don't have enough resources to do everything perfect. Now, a third topic here is privacy. Privacy about protecting our personality. Privacy obviously has not a direct impact on functional safety. Of course, there is a direct impact on cybersecurity. In other words, if we are unable to protect the personal integrity of our data, like where you have been telephoning, what are your contacts, where have you been with the car, if these things cannot be protected, that would mean that we would not be able to conform to basic security needs of the users, of the drivers. Now, the good news is, as I mentioned, that we can benefit from some methodological and also organizational and governance aspects which we need for functional safety anyway. That means the whole risk-oriented functional safety methodology, starting with the HARA, is if you want, one-to-one adapted into cybersecurity. That was 10, 15 years ago when the major security methods were created, that deliberately we used the models from functional safety because they were already risk-oriented, and we transformed them into cybersecurity threat analysis. So Tara looks to threats. A threat obviously has a different, let's say, mathematical connotation because we don't have anything like a probability. In security, we always have 100% probability, but we have things like window of opportunity. So the threat analysis still is risk-oriented because we want to close or reduce the window of opportunity. The impact is, of course, the same in both of them. So the negative consequence, that would be a similar approach. How to mitigate is, of course, different. In safety, we have schemes like redundancy, fail operational. In cybersecurity, we have cryptography, we have intrusion detection, we have, of course, hardening the system, etc. Again, here's a common denominator, which is, for instance, MISRA rules, which we use since many years in functional safety, equally apply with respect to cybersecurity. If you think about zero-pointer dereferencing in Unix or Linux, or if you think in terms of how can we analyze insufficient memory allocation, these topics apply both on safety as well as security. And believe it or not, if we look into the major security threats over the past 20 years, amongst the top 3 is always the same thing. And we speak here about C language because C language still dominates the automotive market. In C language, one of the top 3 major cybersecurity threats has been and will in the near future always be buffer overflow, will be a corrupted input interface. Why? Because many inputs are implemented more or less bottom up, and as soon as you implement something bottom up, you face the risk that there would be errors. I come back on an example later. That means, as a summary from this overview, we can benefit in terms of organization, in terms of process, but also in terms of mitigation, and that makes already a big leverage in order to achieve the necessary efficiency. Now, looking towards the threats which we see in a typical automotive situation, the one most obvious topic is that we have in the meantime a huge amount of interfaces to the outside on different purpose, say, be it diagnosis, be it software updates, be it connectivity for infotainment, etc. And that means all these actually, let's say, advantageous aspects of ACES, of autonomy, connectivity, e-mobility services, create a door because we have a possibility for cyber attack, which, as I just pointed out, can create hazards with respect to functional safety. We should be aware that cybersecurity increasingly is the major liability risk in automotive, and the challenge is that security gaps are not only detected typically quite fast, but in most cases by a third party, and typically also exploited. That's why we speak about a zero-day exploit, because there's not much time. I mean, at the time when somebody exploits and detects a vulnerability, we can be pretty sure that this will not be kept secret or confidential for months to create an update, but we have to deliver very fast. And here's already one important message, which is we will not achieve this objective without over-the-air. That means our vehicles urgently have to migrate into over-the-air software updates, because otherwise we cannot reliably implement cybersecurity. And if you go backwards to what I said earlier, that means our software can be corrupted. The safety-related mitigation, which we have achieved with safety goal and implementation, cannot anymore be guaranteed. And that means any software which can be attacked ultimately will also have a safety impact. And that would mean that product liability is exactly in our shoes as an OEM. including its suppliers, because we have delivered a product which is obviously not on the level of safety as it should be. That means we have here a very close relationship of the current topics in automotive electronics, which is there is a strong need for over-the-air in order to harden our systems with respect to cybersecurity exploits, which is necessary to maintain a reliable functional safety goal. This is a very simplistic equation, but it can be translated: there is no safety without over-the-air. And this is something which we have to consider, because I still see some customers debating how much over-the-air do we need. Now, I don't want to paint it black. Obviously, there are domains in the car. If you have a good network topology, you don't have to make continuous over-the-air updates. You can still use the classic update scheme with diagnostic port. But it means you need a real good topology, which has a domain controller which separates the subnets in terms of very hard firewall and respective policies, so that the threats would not spread into the subnets where you don't have over-the-air. For infotainment, for TCU, etc., there's no way around, because they will have their exploits. We have, by the way, analyzed many of the Linux-driven infotainment stacks with the major suppliers, and we always find weakness. Many weaknesses are in fact due to Linux, because Linux is certainly not the ultra secure operating system. The more open software which is used, the more, let's say, challenge there will be. The good news is there are typically also solutions available, but it also means that the solution have to be distributed, and that is where we talk here about OTA. With that introduction, let me briefly zoom into the standard situation. Standard situation is pretty clear. From a safety perspective, we have the 26262, which dominates. We have still the 61508, specifically in machinery and special vehicles. And we have an increasing perspective into the what we call SOTIF, the safety of the intended functionality for any automated and autonomous functionality in cars. This is the 21448. Now, these are the basic standards which we should know. Now, with all what I said earlier with respect to similarities in safety and security, we can of course also draw the life cycle, which you see here on the right side, already in line with how we can connect these two topics. That is, we have the blue for the security and the orange for the safety. And the standard anticipates that, and that's why ISO 26262 edition 2 did not copy-paste any security mechanism, because that would be highly redundant and also not really useful. It rather refers to TARA and other topics as a shared method. This is an increasing strategy with all the ISO standards to make them modular and refer to each other, so that we don't repeat things as it was in the old days. That makes standards easier to use, not necessarily more efficient if you don't pay attention, because I mean, I see many clients who have huge overhead by replicating security activities in their safety organization, which of course makes not much sense except of wasting money. So here is of course a very close collaboration necessary. The cybersecurity situation is that we have, let's say, three types of standards. There's the classic cybersecurity standards, which is the SAE 3061, also the 21434, which is emerging and will be released soon. Then we have the TISEX, which is the Trusted Information Security Assessment Exchange. That means that is the interface to the IT world. And we do have also the emerging UNECE, which gives clear requirements from a certification perspective, how to ensure that type approval relevant parameters cannot be corrupted by a software update. This has gained a lot of speed since last year, when it was first time released, or 2018 was the first release, but then it was further discussed. This year, February, in the most recent convention, we further made this UNECE software update policy robust. Many OEMs currently migrate into UNECE. We support several of them, and that's of course also an important part of this whole perspective of the standards. So, recommendation very clearly from a vector perspective is, in order to be efficient, connect security and safety. Even being aware that theoretically these are two different things, but still very important that we use existing knowledge, infrastructure, governance, and organization in order to ensure that our safety cannot be corrupted by a security attack. The 21434, which is currently in its DIS review, is following the life cycle similar to this functional safety. You see also a pattern which is pretty similar. The major difference compared to the functional safety is that they spend more energy on Book 5, which is the overall cybersecurity management, as opposed to the project implementation, which is Book 6 onwards, which I think makes a lot of sense because it also makes sure that we have the right security culture. Very clear, like all ISO standards, the 21434 doesn't give any technology recommendation. I've heard many people who said after reading through this standard, it's boring, it doesn't tell us anything. That's normal because it gives us goals. It gives us governance criteria. It does not prescribe how we have to set up an infotainment, how we have to set up a TCU, how do we have to set up a secure OTA. This is not the idea of any ISO standard on that level. It provides us goals and approach such as TARA, for instance. How can we assess security and what are the mechanisms which lifecycle-oriented security has to fulfill? A short word also on the UNECE. These are the legal requirements for cybersecurity and software updates. We have two major UNECE standards which we look at here. One is the cybersecurity related standard, which gives us a very concise summary on topics which you also find in 21434 and in the SAE 3061, which is TARA, threat analysis, threat management, and the need to define the mitigation principles. From perspective of software updates, it's primarily the configuration management with respect to software updates, how to give visibility to the user. This is a new thing that each user or driver of a vehicle must be informed with a software update. What are the impacts of the update? So that is something which we did not do so much in the past. This is now mandatory. Also, the OEMs need to have a full picture of what is the software which is distributed worldwide to different vehicles of a specific type. In other words, must be clear at any moment that software which is distributed as an update, and that can be very fluid updates like continuous deployment of, let's say, specific functionality in autonomous driving cars. All these software updates have to be certified with respect to having no impact on type approval. And especially for legacy, this is not exactly easy. We currently do some investigations and found that the cost in a legacy can easily go in the 3-digit million area. And this is, if you, for instance, go to these requirements of the UNECE, software update management, or SUMS, SUMS, as we say. If you read the 7125, for instance, the manufacturer shall record and store premises for each update at any given vehicle type, the purpose, which are the functions which are impacted, which have a type approval impact. Does the software update impact any of the type approval requirements? Was there any approval available? Is it recorded? So you need a clear traceability from the legal perspective into the functionality, into the delivery to the single vehicle. How the update can be executed, this is the delivery scheme. A confirmation that a software update is done safely and securely. Now, this is now the bridge into the individual vehicle, because you have to track as an OEM that the delivery was complete, that it was correct, and that it is up and running, because there can also be rollback situations and all sort of interferences. And finally, that all this process has passed verification and validation procedures. So that's, let's say, from a theory perspective, very nice and relevant. In practice for legacy, it's extremely expensive, because it means that we have to connect the databases from the legal requirements into the type approval regulations, into the functionality, into the mapping to the ECUs, into the single updates with respect to software. There can be binaries, there can be incremental updates, the calibration data, the respective configuration data, etc. I mentioned already that the good news is that we can connect safety and security. This is what we again show here. The major part is we have two separate tracks, because of course in terms of methodology we have differences, but we have a frequent synchronization. A synchronization point is, for instance, once we have identified a safety goal, the question would be, what is the attack vectors on this safety goal, what would be the respective TARA, and how can we mitigate? And this kind of synchronization points we repeat throughout the life cycle. So we don't do that only on the level of the safety goals. We go downwards into implementation, look into what are architecture cross impacts. We go further down in the life cycle and have a couple of these connections up to the implementation. And of course, as I mentioned on previous slide, for the whole update management after SOP. In a nutshell, the process can be structured. This is a simplified picture where we see horizontally the same as before, vertically, that we have a track which relates to the safety, we have a track which relates to the security, and we have the synchronization points for this initial, let's say, analysis of TARA and TARA, respectively. Now, often we get the question, so how do all these standards relate to each other? The short answer would be the basic precondition for any useful software development process, or generally speaking, system software hardware development, is ASPICE. We strongly recommend an ASPICE level 2 as a basis, because it brings all the ingredients which we need for functional safety and security. Then we have, of course, the 26262, where which you use according to your safety assessment. And we have the specific security standards, the 21434, the UNECE, etc. In terms of shared methods, I mentioned already we have TARA as a shared method, but we also have the MISRA as shared elements between safety and security. We have static analysis like code quality analysis. We have MCDC coverage. In other words, the elements how we achieve security and safety have a high level of overlap. And that's the good news, because that means we can, with an efficient setup of the process, and that's what we currently advise to customers who ask us, how should I set up my 21434 compliant process? Then we take really a picture in terms of how can we best possibly allocate ASPICE 26262 and 21434 process requirements in an efficient way to have the least possible overlaps, to use the same infrastructure, artifacts, and certainly also competencies. Let me give you a few recommendations which we have recently seen in our security projects from an OEM perspective. I think single most important topic, but I trust that this is today not anymore so questionable, means a security manager. Now, what I often see still in organizations, both Tier 1 and OEM, is that there might be a security manager, but it's not so clear how they interfere with the project organization and with the line organization, because obviously a security manager should somehow be connected to the C-level, where you might have a chief security officer or something similar. This organization, in terms of governance, is still not well introduced. Then we see a growing need to align the IT and EE organization that was in the past completely separate. I mean, of course, the IT was contributing in terms of, let's say, cryptographic key management in terms of update management, etc. This is where IT always participated. Diagnostics in the cloud would be another example. But now it's much more important that from the beginning of development onwards, these two organizations are both part of the project organization and contribute together rather than one being somewhere in the, let's say, IT domain, the other one would be in the embedded domain. We speak today about convergence, and convergence means that embedded engineers have to understand IT people have to understand embedded. There's no, let's say, difference anymore between these two domains. Communicate the security strategy and your assumptions to suppliers. That's a major weakness today. All the good ingredients which we have learned over the years in safety seem to be forgotten. We needed a development interface agreement where both parties contribute. It makes no sense if a tier one is in the fork with respect to security strategy. This is more expensive in many cases than if the OEM gets him into the picture. When it comes to key management, it's indispensable. I mean, there's no way around. And of course, then it's clear you have also to make legal obligations. That's understood, of course, by your lawyers. As an OEM, ask supplier to sign a statement. The contractor will observe all relevant standards, laws, legal provision. I mean, this is obvious. It just doesn't help much if we don't have the previous point address, which is share also the necessary insights which we have as an OEM. From supplier perspective, there is no such thing as out of context. We discussed that already in safety. It's in security, maybe even more obvious, because as soon as there are interfaces, there is a context. And if you want to protect the system, complete, then we are exactly at this point, which I called earlier inefficiency. Makes no sense to build security, I should say unnecessary security checks on a component level if they would be already addressed on a level which is more comprehensive. And that means it's helpful to share security strategy between OEM and supplier. The development interface agreement, I mentioned the DIA before, should be available at project start. The OEM to have the TARA security concept interface, etc. The supplier, the derived security concept assumptions. That's one of our key recommendations, that the tier one would periodically perform workshops with the OEM in order to ensure alignment and ensure that assumptions are checked. The overarching topic is, of course, product liability. Product liability is with the organization which brings the product on the market. That's the OEM, but of course, that would not mean that the tier one don't have to do anything. It's more important that both parties understand that what they are doing always have to be sufficiently hardened to also convince a jury in case of a legal lawsuit. So with that overview on the risk-oriented security, let us move onwards to some topics with security engineering. I mentioned before the need for lifecycle-oriented security and the need also to have a TARA at the beginning, derive from TARA the security goals, security concept, the implementation, but then also verify, implement, and ensure that we can deliver. With respect to a security assessment, TARA, we recommend using tools for the simple reason it gives you documentation which looks professional. You can reuse previous assets and also security mechanisms. So specifically, if you have a bigger amount of variation and versioning in your security, then tool support is of a big value as compared to an Excel table. Our Compass in the meantime has been completely updated to a version 2.0, which includes also a quite modern TARA concept with reuse parameters, which will further grow with heuristics and other important needs which we currently evolve. From the TARA, we move onwards into the architecture, into the design, but also the test. So my strong recommendation is to perceive always a test-oriented security requirements engineering that is when we have the TAR on the security goals to discuss the functional security requirements, but also along the same line, think already in terms of what would be the necessary security hardening and security testing, so that when we make updates to the software, we have a minimum viable set of what are the necessary regression test cases which we have to apply on the different abstraction level, from the integration, the fuzzing to the penetration test and the release. Another recommendation is to structure the network in the vehicle so that you don't have to apply the same high level of security, OTA, etc., because some areas are typically not attacked. That means our recommendation is to have several subnets which are protected against each other by strong firewall policy and gateways. Use the domain controller concept in order to make sure that inside the domain you would not have any interference. That's also necessary from a safety perspective. Separate anything which is connectivity related except diagnostics, which we cannot really separate, but everything else should be in a full separate subnet. And those safety critical topics which have some security exposure, such as an OBD interface, etc., that they would have very strong protection mechanism, including some sort of intrusion detection, etc. Security is always a bottom-up design with respect to how do we grow security. That means there is no security which starts somewhere in the middle. Simple example would be if you have a normal software stack with firmware, middleware, application, data, etc., and you would only ensure that the application software is secure, but resides on a middleware which is not secure, that would not help, and that you can continue downwards. That means from the boot sequence onwards, the security has to be running, and that means the boot sequence would be, we call it secure boot, would be the starting point of making sure that the firmware is not impacted, is not attacked, is still consistent, that the different middleware is consistent, and so that during the boot sequence with all its checks, we always build in terms of software which is not in any way changed compared to what was the initial release state and type approval state. Obviously, there are in the meantime a lot of hardware solutions available with hardware security model, trust anchor, etc., which we also support with our AutoSAR. Major suppliers like Infineon provide a lot of excellent hardware-based security solutions. So it's clear that this is mandatory for any of the stacks with a high exposure. That means infotainment, that means ECU, that means also highly safety critical ECU with some sort of a lot of connectivity to across ECUs in the car. Since AutoSAR 4.3, we have security libraries as part of the AutoSAR stack. There are major libraries with respect to crypto, such as crypto libraries, including the HSM connection. Then we do have, of course, still the classic secure boot principles, secure update principles, which are already since a while foreseen. And we have secure communication on board and also interfaces to facilitate this secure end-to-end communication. So we have a complete secure communication stack prescribed or defined in AutoSAR 4.3 onwards, which can start with a secure boot on a secure hardware upwards to the application level. Now, in terms of design, we recommend defensive coding. That means a clear concept for memory allocation, etc. following programming rules like defined in MISRA and CERT. High cryptographic strength, so this is a continuous race, but let's say we should certainly take in the moment 4,000 bit as a minimum key length because the protection which we use is typically always depending on what are the tools which attackers would use, and with the growing speed of brute force, password crackers, etc., we also have to increase key length, and that gives us always a race with respect to what the minimum length would make sense. In terms of right side of the V, verification validation, we have static dynamic code analysis, we have unit testing, MCDC coverage, we have interface scanner, fuzzy tester, encryption cracker, vulnerability scanner. So that would be typical tools which are used in, let's say, classic Ethernet-based architectures since a while, but also now with the growing usage of these IP techniques in the car, also can be reused. Obviously, these tools are also available for classic protocol stacks. So we have extended our canalizer and other tools in this domain. Finally, a word on penetration testing. I mentioned earlier this is a big benefit because fuzzing and penetration tests are the test methods which we strongly recommend, and we also provide the necessary environment for that. This is summarized here with the different, let's say, verification techniques, and starting with CQA on the bottom, code analysis, fuzzing, pen test, then also protecting the updates, and software update management following the UNECE. One word on UNECE, because we often get the question, what is the reference process? In a nutshell, it's a handshake between the legal requirements that's in this picture, in the process number 1, into a mapping to functionality, into a mapping of implementation within the ECU, and then the whole sequence of transmission to the vehicle. And finally, the handshake, the vehicle has received the update. OEM knows that the vehicle has achieved a successful update. It takes the record. Driver can be informed, and the OEM has in its vehicle database that the upgrade has been successfully performed. In terms of project experience, a few snapshots. A security check is certainly the typical starting point for those which are rather new to cybersecurity, which we typically do for OEM and Tier 1 in the beginning of projects, where we look into architecture, into security concepts, into competencies and the processes, give advice, what would be the low-hanging fruit, what are the biggest risks in order to facilitate a smooth evolution path. Second, we implement cybersecurity-related development processes in the meantime in many companies, either with a link to 21434 or just in a standalone mode. Also Agile with cybersecurity is today done. Finally, pen test. We have grown our labs in this direction to provide the necessary pen test services with good success, because as I mentioned in my introduction, we have started with gray box pen test, which allows also to deliver an efficient pen testing. With that being said, let me summarize along what I try to convey during this webinar. We have on one side a need for risk-oriented, holistic safety and security-oriented engineering. That's the upper left here, with a systematic process following the necessary standards of 26262 for safety, 21434 for security, UNECE for update management, and then ensure that the supply chain is closely connected. That's this IT convergence. We are able to monitor our updates in the car, which is the UNECE perspective, and make sure that we have the necessary provisioning, also supervision services like the PSIRT as recommended by CERT. And this means we can really deliver lifecycle security, including scalability from is designed for security up to updates, regression, and services, but also with different type of operation, such as attack modes, emergency modes, etc. Also here we have an overlay of safety security. In safety we have the fail operational scenarios. In security we have on top of that the different security operational modes which provide fallback possibilities. Vector certainly provides a quite comprehensive portfolio with tools, with base software, with services, with a lot of interfaces to the major hardware vendors. So if there you see needs, just contact us. More information you find at www.vector.com/security. Specifically with respect to our worldwide project experiences, you find here links to our webinars and podcasts, to our trainings. There's a lot of white papers which are available, and the before mentioned tool, which is www.vector.com/compass. And with that being said, I guess the one advice which I want to emphasize is don't take cybersecurity easy. The cartoon here shows maybe sometimes it's taken a bit too easy with the here encryption, but could be also in other domains. We see in practice a lot of process weakness. In fact, the technical weaknesses are much less compared to process weakness. Insufficient competences, insufficient training, insufficient code quality analysis, etc. And with that being said, I suggest that we hand over to my colleague Youssef Rekik, and he will address some questions which we received during the webinar.
Thank you, Christoph. We definitely received a lot of interesting questions. So maybe I can start with the first one is about the participants asking about the Compass software. So it's actually standalone software, not connected to other vector tools like Provision. And as Christoph said at the end, you can download it from vector.com/compass. You can also request a demo license there. The second question we received from a few participants is about the risk value rating in ISO 21434 compared to J3061. And we also think that the adoption of ISO 21434 is very much needed. And as it is, we are currently supporting multiple suppliers and OEMs with the implementation of the ISO 21434 processes, including some trainings on the new risk methodology and the new risk calculation. So the impact rating is widely known. So we know it before from the J3061. It can be severe, major, moderate, or negligible. And it's based on impact categories of safety, functional safety specifically, financial, operational, and privacy. And the safety-related impacts can, of course, be derived from the ISO 26262. The second factor in the risk value rating is the attack feasibility. Here, the ISO gives a recommendation for 3 options for the attack feasibility rating. First one is the attack vector methodology. It's very low if it's physical, it's medium if it's adjacent, it's a high attack vector if it's, let's say, a network-based attack. For example, an attacker compromises a navigation ECU from cellular interface down to the gateway ECU to forward malicious signal to a power switch actuator, for example. And that is a high attack vector and a high feasibility attack because it's on a network level. Second example would be that from the OBD2 connector, you can forward some signals to the power switch actuator. And in this case, it's low because you have to access the OBD2 connector, but it's not at the same time very low because you don't require access to internal ECU components. The second option to calculate the attack feasibility is based on the attack potential. So here the ISO also gives quantified values and guideline on how to calculate this based on the elapsed time, how much time do you need to do and perform this attack, what is the expertise needed to perform this attack, is it someone who is a layman, does not know much about the automotive industry but can follow tutorials, is it an expert, and how much knowledge does he need of the ECU that he's trying to attack. Is it public information? Is it shared knowledge? And or is it, in this case, some confidential information he needs? The fourth factor would be the window of opportunity. Is it in limited time? Is it easy? Is it, let's say, a moderate window of opportunity to perform this attack? And the fifth factor would be the equipment he needs to perform this attack. Is it commercial, off-the-shelf equipment, tailored equipment, or standard? So 5 factors to calculate this: elapsed time, expertise, knowledge of the item, window of opportunity, and equipment. The third way to do it is through this common vulnerability scoring system, CVSS, that's maintained by FIRST, and it's based on the attack vector, attack complexity, privileges required, and user interaction. And these 3 options will help us then calculate this attack feasibility. Once we know the attack feasibility and we know the impact rating, we can then map this to the risk value calculation. The risk value then is mapped to the cybersecurity assurance level, the CAL, from CAL 1 to CAL 5, where CAL 4 and CAL 5 are the highest risk value. So this is the question about the risk value calculation. A third question we got is about why ISO 21434 does not define CAL and its impact on the engineering process, as done in ISO 26262 for safety with the A0 rating, but instead leaves it to be defined by the organization. So actually, in the ISO standard, there is no clear, there are no requirements in the standard, but in the annex, we have examples and guidelines how the CAL level can define the following processes and what is needed in terms of verification, validation, concept phase, security testing. And then it's up to the organization to adopt and tailor these processes to their normal way of working. As an example, if we have the cybersecurity assurance level 1 for a security requirement, then developers or users require a low to moderate level of independently assured cybersecurity, and it requires developer testing and vulnerability analysis, for example. If it's a cybersecurity assurance level 4, which means the risk value here is high, then developers or users require the highest level rigor, advanced methodologically designed, tested, and reviewed, independently also tested and reviewed. For example, an add-on independent vulnerability analysis by a third company. This Annex E also gives example in the concept phase, the cybersecurity requirement that is allocated to the STARA scenario, of course, inherits its cybersecurity assurance level, its CAL value. Then when that security requirement is allocated to an architecture component, the architecture component also inherits the cybersecurity assurance level. And then this will affect, for example, verification methods of architectural design. Cybersecurity assurance level 1 and 2 will only need review and analysis, but if you have a higher CAL, 3, 4, or 5, then we will need in addition simulation and prototyping. In the meantime, we also received a lot of important questions in the Q&A, so I will continue to answer those questions offline, and I will hand over back the ball to you, Christophe, to close the webinar.
Thank you, Youssef. This was very insightful, and seemingly you received tons of questions, so good luck with finalizing. And to all of you who listen to this webinar in a recorded fashion, here are the coordinates how you can reach us. www.vector.com/consulting. Also email, also Twitter, which I recommend if you want to stay tuned to further events, also to white papers, etc., which we publish, practical advice. Don't overdo like some other people's on Twitter. So we have like 1 or 2 tweets per week, but they are really profound. So connect with us. And for all of you, both online and listening remotely, wish you good success with your cybersecurity projects. Don't hesitate to contact us with respect to building up your security process, hardening your system, pen testing, doing the TARA, and of course also our products here in Vector, like the AutoSAR stack or like tools which we use in testing. So thank you very much, and good success, and hope to talk to you soon again. Bye.